Shoshanik, Program Manager at Microsoft. Here to talk to you a little bit about a new service that we're offering called HPC Cache. It goes GA as of this past Monday, and we're really excited to talk to you about it and answer any questions you may have after the fact. We're going to go over some of the reasons why HPC Cache exists. We're going to talk a little bit about the details of what the service would be and how you would use it and how you'd consume it, what options you have in terms of file systems, and then ultimately call to action about being able to access it. And I know it says public preview. It didn't on my slides. It's GA, but just you can reach out to me and talk to you about access. So first things first, why does such a thing exist? For those of you that have a lot of unstructured data, whether that data is images or movie rendering content or assets, driving data. If you've ever seen the autonomous vehicles with the LiDAR, that generates a tremendous amount of data. And that data typically needs processed by some sort of HPC environment. HPC clusters running on-prem, been around for a long time. Nothing there is going to change necessarily. But a lot of people now are faced with the reality that there's simply more data and more processing than there is physical space in a data center. And so to be able to refine their use cases to be complementary into the cloud would be great. You can see we're talking about the amount of data being generated up to 100 gigabytes of data for a human genome. I work very closely with a lot of life sciences use cases, and I know that this is really only the beginning of the data that's going to be generated in this space. It's going to be significantly larger than that over time. However, most of the workloads today are still on-prem. Most of the data for those workloads are still on-prem in data centers. Why? Why not? There's no compelling interest necessarily, or there hasn't been, to move everything concurrently into the cloud. Because it will take a lot of work to do that, and it takes a lot of impetus and business case and drivers to move that data to the cloud. So ultimately, you have to make a decision. Am I going to rewrite the data, rewrite my applications, push everything into the cloud? It creates a lot of political wins and debates and technical challenges. And so ultimately, you have to be conscious that people have invented the on-premise environment. It's the way it is. And to move the data into the cloud is really a big challenge, unless you consider things like the HPC cache. So I'm going to identify 4 aspects of the challenge in terms of data access as these 4. I'm going to start with latency. So being able to run compute in the cloud is incredibly simple compared to what it used to be 6, 7, 8 years ago. So with a few simple scripts, you can set up a full 100-machine cluster with disks and networking and everything else, and you can do it in relatively short order. And so the ability to take your jobs that you have been running on your bare metal in your data center and transporting them into Azure Compute to run is very much within your grasp, and it's fairly straightforward, relatively easy to do, comparatively speaking. However, if I run a 100 VM environment and those VMs all come up and they're going to read libraries and tool chains that are sitting back across a wide area network connection in a NAS environment, there's going to be this buildup of latency. Each request is going to take some amount of milliseconds round trip time. And that's going to build up and create what we call back pressure. That in turn will slow down the overall job, which I typically call analytic latency. And so the whole job slows down. And that's been one of the reasons that people, they have a lot of compute power on-prem, they have a lot of data in their NAS environment. To put it in the cloud has always been a little bit of a leap because of that latency. How do I overcome the latency? And yes, there are ways to overcome that latency without a cache. One of them would be to copy the data into the cloud, which is down there under consistency. However, in the case of consistency, what I'm referring to there is I can copy the data up, and I can put it on every disk, on every machine in my compute cluster, and I can run my jobs. However, if changes occur to the data that's sitting on-prem, how do I know to synchronize that data into the cloud? And so you have this sort of change management operation that you have to bring in, and that's where things like sync, mirror, and other capabilities would be relevant. However, even there, you have to add additional technology on top of it. And so even if you can copy all the data up, you still have a physics problem of getting it across the wide area network, and then you have a consistency problem with making sure that you're running with the latest data. Throughput refers to the fact that in order to get to the cloud in the first place, I have to have something like an express route. And so I can get a 1 gig or 10 gig or something in between express route and move my data up there, and that's fantastic. But if I'm in an enterprise, I may not be the only user of that link. And so I have to make sure that at the time that I need the data or the throughput, that there's not a saturation of that link. If there's a saturation of that link, I go back to the first thing I mentioned, which is latency, and I start all over again with the challenge. And then last thing is scale. So one of the powers of HPC clusters is that you have been able, over the years, to build up an impressive array of bare metal servers in your data center at scale, running very quickly. You have the programmatic capability to do that in Azure today. You can launch any number of compute in a cluster running HPC with a scheduler, just like you do on-premise today. But the scale must be matched by the scale of data access. And so I need to be able to make sure that if I'm running 100 machines or something greater than that, I get the same general latencies and throughput capability that I would expect on-prem, or at least near it. I want to bring up another challenge that caching specifically addresses, and that's something called hotspotting. So at the bottom, you'll see 3 different references to Isilon NetApp and then a parallel file system. So in each case, there are circumstances where you can end up with what's called hotspotting, which is a concentrated focus on a single file or a group of files and a set of metadata about that file by a large number of machines. And each one of the architectures has some amount of, I don't want to call it limitation, but under the right circumstances, it can create back pressure, which then increases latency and slows down your jobs. And so each one of these exhibits, in the case of the NetApp-like approach, the data and the metadata are coexistent on a single node in the NetApp cluster. If I get enough concurrent access requests of that particular file and that particular set of metadata, that's going to build up into back pressure, which is called hotspotting. And then in the case of Isilon, I might stripe the data, but the metadata is concentrated. And so I may end up, if I have a job that does a lot of navigation of directory structures and access of file information, that can then create also additional hotspotting and back pressure. And then finally, if you look at a parallel file system, which are very fast, you can run Lustre, you can run GPFS. However, they have a metadata server. And so hopefully you size the metadata server to handle the level of demand that your job needs. If you don't, you can end up with a focused concentration on that metadata server that again in turn creates that hotspotting. And we've seen this in customers that run very large workflows, 50,000 core workflows, where they had to stop using it because it was just hotspotting too much. So you have throughput, you have consistency, you have scale, and you have latency management. And so why we invented Hpc Cache is to address these things, at least for a certain tier of use cases. So the first thing is, it is a high-performance, clustered cache for files specifically. And we have made it as simple as 3 SKUs, and I'll show you the SKUs in a minute, that you can choose from that sort of tune what sort of performance and what sort of caching that you need. Distributed scale. So when you set up an HPC cache, it will present you then with a set of IP addresses, depending on which SKU you choose. And those are your mount points. And then you use simple round-robin DNS to distribute your clients across those mount points, and you have high availability. If any one of those IP addresses becomes unavailable, it is automatically failed to, those clients are automatically failed to another endpoint, and they continue operation. Flexible access. I'm going to talk a little bit about that. The thing that makes this unique, and this is really the first offering of its kind in the cloud, in any cloud, is that it has the ability to not only reach back and grab data from your on-premise NAS, but it also has the ability to present that data in a way that's basically one directory structure. So your clients will mount one mount point, we virtualize file IDs out the front, you can start plugging in other sources of data into that same directory structure, and it will continue to operate. You don't have to unmount your clients. And then lastly, easy to integrate. This is a first-class Azure service in the portal. I'll talk about that a little bit later as well. But it's meant to be as simple as possible. You set it up, you point at your storage sources, and you run. These are the SKUs that I mentioned. So again, in the spirit of trying to make it as simple as possible, the choice you make, these are literally the SKU names. Pick the bandwidth that you need. right? So up to 2 gigabytes per second, 4 gigabytes per second, or 8 gigabytes per second. Those are today's SKUs. We're going to take it as we go, get feedback from the field and customers about do they want more than that? Do we need something in the middle? But those are the 3 SKUs that you'll get. When you get those 3 SKUs, after it's done setup, it'll present you IP addresses that you can mount. Those are the different IP addresses. And then you see these cache disk sizes. And so the reason that we have cache disk sizes on here is, let's say your scenario is that you're running a compute job in Azure Compute against some data sitting in your NetApp environment on-prem. And let's say that that working set, that data that you're requesting, is 10 terabytes. So you would want to make sure that you select the cache size that matches that working set, so that if you start to run out of disk space, you don't get this flushing recurrent access of that data. And so you have fine-grained control over the amount of local caching space that HPC Cache will make available for the jobs. All right, so when do you use HPC Cache? You'll see I make a reference to VFXT at the top. That is the predecessor to the service. It is the Azure VFXT appliance. It's a set of virtual machines. You can get the Azure VFXT appliance through the Azure Marketplace. And if you have any other questions about that, you can see me after, we can talk about it. So when do you want to use this? So it's really essentially that the client wants to run HPC workloads. There's a significant number of clients, and then you have these conditions. There's an on-premise NAS environment, or it can be an Azure NetApp file volume or volumes that you need to access. I'll give you an example of what I mean by that. You set up an Azure NetApp Files volume. Let's say it's in East US, and you have a compute cluster that you want to run in West US too for some reason. You can run an HPC cache in West US and access that data and present it. So it gives you a way to go past that and reduce your overall access cost. The data is mostly large files. And why I'm qualifying this here is that if you have a workload that consists of 10 billion 1K files, that's not a really great workload for a cache, because it's a significant amount of data and it creates a lot of volatility. There's a significant amount of metadata that has to be dealt with in that particular mix. Workloads in our circumstance can be mixed. So you can have a read-heavy workload that reads libraries into place. You can do writing out. The place that you wouldn't use an HPC cache necessarily is if you have an ingest application. That's all it does, is ingest vast amounts of data into the cloud. That's a whole different beast. It's not a cacheable workload. But also, customer wants to use Blob because of the low cost of Blob, but you need full POSIX compliance. You have hard links in your workload, and you need to make sure that those are supported. Customers running a parallel file system on-prem, but wants to get their feet wet running in Azure Compute, doesn't really want to incur the complexity of running a parallel file system yet. Fine, throw up the NFS daemon on your Lustre environment and access that through the HPC cache. And then your performance expectations are in this range, okay? So what you wouldn't use this for is if you want to put up a Windows share with home directories. Not a good use case. This is architecturally what it looks like. And this is kind of interesting because ultimately the HPC cache doesn't exist per se inside your subscription, but the network does. And so this gives you the ability to have a simple, easy, managed environment that has network access to your on-prem data, as well as, in this case, Blob, if you need the POSIX requirement. But the interesting thing about it is it's in your network. There's no way for anybody to access the HPC cache except through your network. So even when we're troubleshooting, if we have to troubleshoot, we can't get in. We have to go in with your permission. And so it's a highly secure, closed-off environment that has the ability to get that data. It has a single management plane. So what this means is you're running an Azure portal. You can create multiple HPC caches. You can even point those multiple HPC caches at the same data, at the same export. Because from the NAS perspective, from the NetApp or the Isilon or whatever you're running's perspective, HPC cache is just an NFS client, right? The intelligence is on the front end of the cache and how we manage the data and how we present that data to the clients. I mentioned the hotspotting problem before. So when you have concentrated access of data and metadata. So HPC Cache actually propagates the metadata across the caching surface. And so there's no single point necessarily that all clients have to go to get that metadata information. And this eliminates hotspotting in the vast number of cases. Every now and then you'll get a hotspot, but then it settles out once the access pattern is established. This is what I mentioned before. So we have the ability to use Blob. However, the customers that we have worked with historically need full POSIX compliance. So they have a pipeline. The pipeline has hard links, soft links, all kinds of different things. They need to make sure that that is supported, but they want the nice low-cost capability that Blob offers. They want the ability to maybe tier that off into some lower-cost layer over time. So they want everything. They want the cost of Blob, but they want the performance. So this is in advance of ADLS Gen 2 with the NFS endpoint. But this exhibits the number of NFS operations that we have to translate into actionable object commands. And so we take all of these different operations, these are the RPCs that NFS does, we translate those into basically the 4 primary Blob operations. And that's how you get what we call Blob as POSIX. It gives you full capability. And I just highlight this because there are tools out there, if you're familiar with like Fuse type applications that sort of simulate using a file system on Blob. The reason that this is the way it is because this is a very precise. If you change, if you rename something, that rename has to be reflected up the directory structure. Well, directory structure doesn't exist in Blob. Those are individual objects. And so if you change something deep in a directory structure, it has to be reflected all the way up the stack. Okay? But not only do we support Blob as POSIX, but we support other backends such as C-mode NetApp or 7-mode NetApp, Isilon. So you can basically set this up, point it at an IFS mount, and present the data from your Isilon environment. This is the flexible access nature of the product. The service will provide you the ability to define what we call an aggregated namespace. And what's powerful about this is I may have more than one NAS environment on-prem. I may have a NAS environment on-prem and I may be running an ANF volume. I may have both of those and also have a desire to put, for example, reference genomes or other data in a Blob container for presentation to my compute cluster in Azure Compute, just to save on the latency and also the costs, right? So this gives you the ability to create a whole directory structure, but pointing at discrete individual sources of data. And you can support up to 10 unique sources of data in this aggregated namespace. What that means is up to 10 NetApps, but within those NetApps, there can also be additional exports. Those can also be put into leaf nodes in your aggregated namespace. So you can really have a quite deep and broad namespace represented for the clients. Okay? And the nice thing is you can take things out of the namespace, put things into the namespace without having to mount or remount the clients. Okay? All right, client access, this is very straightforward. This is just talking about how do I mount this HPC cache. I start it, I either mount it directly with the IP address, or I set up a DNS host with multiple entries for those IP addresses. That gets you what we call round-robin allocation of those accesses. We have this thing called usage policies, and so this is how should the cache behave with regards to the data. In other words, is the data being written behind the cache, and therefore the cache needs to check the M times of all of the files that it's accessing. If it finds a deviation in the M time, go and fetch the data from the back end. Or, I don't care about that, go as fast as you can, don't worry about checking it, let's just present the data. And so we give you the ability to control those usage policies. I'm going to not spend a lot of time on this, but we have behind the scenes, trust me, thousands and thousands and thousands of stats, but we've made it simpler for you so that you could see only the essential stats that you need, and that is fully integrated into Azure Monitor. ARM API integration, so you can use everything today except Azure CLI and PowerShell. Those will require a little bit of time on our part. They are roadmapped for onboarding, but there's already a Python API and ARM integration. I'm going to tell you that we have cache states, and I'm going to skip that because we're almost out of time. And one last thing. So this is a cache. It resides in your environment. We are a first-class service. We follow all the rules and all the guidelines of a first-class service, including how we upgrade the HPC cache. And so this is a full, the thing to think about here is this is a full managed service. There is a team behind this. That team monitors your environment, makes sure everything's stable. If something is disrupted in your environment, they're engaging with you to take action on your behalf. To take care of that. But also, as we improve the service over time, the cache will need upgraded. And so we give you the control to do the upgrade within a reasonable window of time, but at your discretion. And last thing to mention to you is, I mentioned that blob is POSIX format. So one of the challenges would be if you have data that you want to bring up into Azure and you want to put it into blob, but you want to do it as fast as possible and you don't want to have to wait a long time for that. We actually build a utility. This utility will be added to AZ copy as soon as possible. And it will allow you to directly plug data into a container already as this blob as POSIX format. So what that will allow you to do is, let's say you have 20 terabytes of data and you want to get it up there as fast as you can. This tool will go, I'd say roughly 7 or 8 times faster than an rsync would. Push it up there as fast as you can. You don't even have to set up your HPC cache yet. Once it's done, then you turn on your HPC cache, point it at that container, and you're off to the races. With that, I thank you all very much for your time. If you have any questions, stop by. Thanks.